Okay, so in the previous lecture we talked about connected components, and today we are going to introduce a notion of path connectedness, which is like a more intuitive notion of connectedness. So let's just see what this is. Okay, so definition. Okay, so this path connectedness. Okay, so let X be a topological space. And we say X is path connected if for any 2 points X and Y in X, there is a continuous map gamma from 0, 1 to X such that gamma of 0 is equal to X and gamma of 1 is equal to Y. Right? So if you make a picture, so our topological space X might be like this is X and this is Y, and then there's some gamma which could be very complicated, which connects X to Y. Okay. All right. So the first thing we want to prove is that first result we want to prove is a path connector space. A path connector space is connected. Okay, so being path connected is a stronger notion than being connected. So proof. Right, so let us assume that X is path connected but not connected. Right, then since it's not connected, we can write X as a disjoint union U disjoint union V, right, where U and V are non-empty open subsets. Right. So since they are non-empty, right, let X be a point in U and Y be a point in V. Right. So then, as X is path connected, there is a continuous map gamma from 0, 1 to X such that gamma of 0 is equal to X and gamma of 1 is equal to Y. Right. So now we simply take, so the inverse image, right. So then 0, 1 we can write it as gamma inverse U disjoint union gamma inverse V. Since U and V are disjoint, their inverse images are also going to be disjoint, right. And 0 is in gamma inverse U because gamma of 0 is equal to X, which is U, and 1 belongs to gamma inverse of V, right. And both these are open, so thus we have written 0, 1 as a disjoint union of non-empty open subsets. So they are open because gamma is continuous, and therefore the inverse image of an open subset is open, right? So this contradicts the connectedness of 0, 1. Okay. So a path connector space is connected, right? So this completes the proof. Right. So let's see some examples. So 0, 1, all these nice examples that we know are all path connected. Right. So I mean, if we take the interval 0, 1, right, so then any 2 points A and B, we can join it by a straight line, right? So we can define gamma of t is equal to 1 minus t times A plus t times B. Right. So this is then gamma is a continuous map from 0, 1 to this interval 0, 1, such that gamma of 0 is equal to A and gamma of 1 is equal to B. Right. So any 2 points can be connected by this path. So the same works for the same gamma works for shows that R and Rn are also connected, are path connected. Right. So for Rn, we can just take 2 vectors, right, and we can join them by a straight line once again. So gamma is 0, 1 to Rn, and this is gamma of t is equal to, let's say we have 2 vectors A plus t times B. Right. So let's look at S1. So S1 is this circle over here. So once again, given any 2 points, let's say this is at an angle theta 1, and let's take another point here, which is at an angle theta 2. Right. So this is A and this is B. So then we can connect. So the point is we can connect using a path which starts at A and goes all the way here, right? So but if you were to write it explicitly, so then we can define gamma of t is equal to e to the power 1 minus t times theta 1 plus t times theta 2. So we have defined this map gamma t, and we need to show that this is continuous. So we will write it as a composite of 2 continuous maps, right? So we have this map from 0, 1 to R, which is t goes to 1 minus t times theta 1 plus t times theta 2. Right. And then we will take the map from R to C, which is x goes to e to the power x. Right. So this map is continuous. Right. And therefore this composite is continuous. Okay, so let's try to see that the spheres, okay, so this is S1, but how about the spheres, right? So let's just do the example for S2. So for S2, right, let's say this is the equator. This is the north pole, so let's call it N. And this is the south pole, this is S. Right. So if P is any point which is not equal to the south pole, then what we can do is we can connect. We can take this point P. Right. We can join by the straight line, right? So first we consider this path gamma 1 t, that is equal to t times n, or rather 1 minus t times n plus T times P, right? But now the straight line is not going to lie on the sphere, so P is not equal to S, that is important. So, so we have to make this lie on the sphere. So for that, note that 0 does not lie on the straight line, right? The origin. So maybe I should write 0. Right. So then this implies that the norm of gamma 1 t is a continuous map from 0 1 to R, right? And therefore we can just define this map gamma 1 t by norm of gamma 1 t. Right, this is from 0 1, and the image now will land inside the sphere S2. So what is this map? This map is t goes to gamma 1 t divided by norm of gamma 1 t. Okay, this is continuous, so this is actually, this goes to positive reals. Yeah, this is continuous because we are taking a continuous map and dividing it by another continuous map, right? So each of the coordinates of gamma 1. So if I were to write this as gamma 1 1 t is divided by norm, right? Each of these coordinates is a continuous map because the denominator is never 0. Right? Okay, so this shows that, n can be connected to any point P using a path. Right? Now, but we want to connect n to S, the south pole also. So for that, I mean, we can just take two paths and just join them. So we can take this point. So first we can connect n to this point, and then in the same way that we constructed this path from n to a point P, we can construct a path from the south pole to the point P. So this gives a combined path from the north pole to the south pole, right? So this shows that. So this shows that S2 is path connected. So how to combine two paths is something which we'll see precisely in a minute. So, and the same proof can be slightly modified. So a slight modification of this proof also shows that Sn, right, a slight modification of this proof shows that Sn is path connected for all n greater than equal to 1. Right. In fact, this proof is better because then we don't have to worry about x goes to e to the power x is continuous. Right? We can just do away with that. Okay. So we have seen some examples of path connected spaces, some nice examples where we actually make some pictures and intuitively imagine. Okay, so but now let's continue with our discussion. So as before, okay, so before we continue, like we can also ask ourselves, so we have seen many spaces so far, so what about the path connectedness of those? So what are the other examples we have seen? We have seen GL and R, we have seen M and R, we have seen the orthogonal groups, the special orthogonal groups, we have seen the unitary matrices SU and right. What about connectedness of these, right? So GL and R is not even connected because we have this determinant map from GL and R to R minus 0, right, which is surjective. because we can just take minus 1. Determinant of this is minus 1, and of course determinant of the identity is plus 1, right? So therefore r minus 0, which is disconnected, we can write it as u disjoint union v, where u is this half open interval and v is this half open interval, right? And this is the point 0 which you're missing out. So when we take, so the determinant is a surjective map from GL and R to, in fact we can just put any lambda over here, lambda non-zero. So we get this surjective map. So this implies that determinant inverse of u, disjoint union determinant inverse of v, both are non-empty, gives a, so we can write GL and R as the disjoint union of two non-empty open subsets. So therefore GL and R is not connected, right? So, but on the other hand, we can ask, what about GL and R plus? This is equal to those matrices A in, or this is just equal to determinant inverse of matrices with positive determinant. Okay, so we will show that later. This is path connected. Okay, so M and R is just R n square, and this is a vector space. So since Rn is path connected, that same proof gives that M and R is path connected. Once again, the orthogonal groups are not path connected for the same reason, because when we take determinant, the determinant, it lands inside this set plus minus 1, right? And this plus minus 1 is just 1 disjoint union minus 1, and once again the determinant is surjective. So when we take the inverse image of both these open subsets, so we get, that shows that On is not connected. So On is not connected. So it's important to say that the determinant is surjective, because if you look at, if you look at GL and R plus, so let me just write GL and R is not connected, right? So when we look at the determinant map at the level of GL and R plus, the image lands inside minus infinity, comma 0, disjoint union 0, comma infinity, right? But when we take the inverse image of the determinant, determinant inverse of minus infinity, comma 0 is empty over here, right? So therefore this does not show that GL and R plus is disconnected. So what I'm trying to emphasize is, it's important to say that this map is surjective, or at least it meets the components of more than one component of the target space, right? More than one connected component of the target space. Okay, so but SON, so ON is not path connected, is not connected, yeah, but SON is path connected, right? Similarly, UN and SUN are path connected. So these three examples are very interesting, but they are also difficult to prove. And to prove these, we need the notion of quotient topology, which we will introduce later on in this course. So we will, towards the end of this course, we will prove that these three spaces are path connected. And I should say that one should emphasize this result, because it's very interesting, because SON, is defined as, it has a very complicated definition, A transpose is equal to identity, and determinant of A is equal to 1, right? So with this complicated definition, a priori, if one just looks at the definition, it's not all clear if it is path connected. But yes, we can join any point, any 2 points in SON with a path, which is completely inside SON. Okay, so now let us continue. As before, we define an equivalence relation on X. Okay, so this time, we define the relation as follows. So we say that. So we define X is equivalent to Y if there is a path from continuous map from 0, 1 to X such that gamma of 0 is equal to X and gamma of 1 is equal to Y. Right? So this is new equivalence relation, and let us check that. So let us check that this defines an equivalence relation. Right? So we need to check three things. So first we need to check that X is equivalent to X. Right? So this is easy, so we just take the constant path. Right? So in other words, gamma from 0, 1 to X and gamma of t is equal to X for all t. Right? And the constant path is continuous. So the second is, if X is equivalent to Y, then Y is equivalent to X. Right? So suppose, since X is equivalent to Y, there is a path gamma such that gamma of 0 is equal to X and gamma of 1 is equal to Y. Right? So then take gamma 1, define gamma 1 of t is equal to gamma of 1 minus t. Right? So gamma 1 is the composite of 0, 1 to 0, 1. This is t goes to 1 minus t, which is obviously continuous, and then here we have gamma. Right? So gamma 1 is a path from, gamma 1 is a path from Y to X. Okay, so basically if this is gamma, this is X, this is Y, so gamma is going like this, then gamma 1 traces it in the same path in the opposite direction. So in particular, gamma and gamma 1 have the same image inside X. They are different maps from 0, 1 to X, but they have the same image. Okay, and the third thing we need to check is, if X is equivalent to Y and Y is equivalent to X, then X is equivalent to Z. Right? So here we will use a theorem that we learned some time back. It is about how to check continuity of a map by restricting it to two closed subsets. Right? So since X is equivalent to Y, we have a path gamma 1 from 0, 1 to X, a continuous map such that gamma 1 of 0 is equal to X and gamma 1 of 1 is equal to Y. And since Y is equivalent to Z, we have this path. This is gamma of 1. Sorry, this is gamma 2. Gamma 2 of 0 is equal to Y and gamma 2 of 1 is equal to Z. Right? So basically this X, this Y and this Z. Right? So here we have gamma 1 and here we have gamma 2. Okay? So now we define this map from H. Okay, first we define a map from H1, 0, half to X. So H1 of t is equal to gamma 1 of 2t. Okay, and then we define a map H2 from half gamma 1 to X by H2 of t is equal to gamma 1 of 2t minus gamma 2 of 2t minus 1. Okay, So let's check that h1 of half is equal to h2 of half, right. So is this equal? So h1 of half is gamma 1 of 1, which is equal to y, and h2 of half is gamma 2 of 0, which is also equal to y, right. Therefore, they are equal, right. So now this, what does this mean? This means that on the interval 0, 1, this half, right. Let's call this set A and let's call this set B, right. A is the closed interval 0, half, and B is the closed interval half 1, right. So this to x we have defined this map. So this map is h1 on this 0, half, and it's h2 on half comma 1 on B, right. So this defines a map H, and this map is, I mean, this actually defines a map because both the only point of intersection, so h1 is a map on A and h2 is a map on B, and both h1 and h2 agree on the intersection. In this case, the intersection is just the point half, right. So therefore, it defines a map. We get a map of sets right now H from 0, 1 to x. So the question is H continuous? Right. So now recall our theorem, right. So H is continuous. So since, right, A comma B contained in 0, 1 are closed subsets, a closed subset, right. So H from 0, 1 to x is continuous if and only if H restricted to A and H restricted to B are continuous. So obviously A and B have the subspace topology, right, but H restricted to A is exactly H1, right. And what is H1? H1 is the composite. So first we go from 0, half to 0, 1, t goes to 2t, right, and then we apply gamma 1 to x, and gamma 1 is continuous and this map is continuous, so therefore their composite is continuous. And similarly, H restricted to B is equal to H2. So what is H2? First we go from half comma 1 to 0, 1 by t goes to 2t minus 1, and then we compose with gamma 2. So gamma 2 is continuous, this map is continuous, the first, this t goes to 2t minus 1, right, because we have seen that all polynomials in the coordinates are continuous. So therefore this composite is continuous, right. So this implies that H1 restricted A and H restricted A and H restricted B are continuous. This implies that H is continuous, right. So moreover, H of 0 is equal to, so H is defined to be H1 on the interval 0, half, right. So H of 0 is equal to H1 of 0, which is equal to gamma 1 of 0, which is equal to x, right, and H of 1 is equal to, so H is defined as H2 on the interval B, so it's H2 of 1, which is equal to gamma 2 of 1, which is equal to z, right. So thus H is a path from x to z, right. So this shows that x is equal to z. Okay. So and this also shows if I have topological space X and if I can join 2 points x and y with a path and y and z with a path, then I can join x and z with a path, which is precisely what we used over here in the example of the sphere. So we can join the north pole to any point P, and then so we can join the north pole to this point P, right, and then P we can join to this point S, right. So therefore, we can join the north pole to S. Okay. So this defines an equivalence relation. On X, right? So the equivalence classes are called the path components of X. Okay, and similar to the proposition about connected components that we proved last time, we have this proposition about path components. One, every path connected subset. So okay, so we can write X as a disjoint union of Xi's. Now Xi's are path components. Right? Every path connected subspace of X is contained in some Xi. In fact, it's contained in a unique Xi, right? And 2, each Xi is path connected. Okay, so both these will prove that Xi are maximal path connected subspaces of X. Right. So notice that earlier we had a third point which said that when we looked at the connected components, we had that the connected components are also closed. Yeah, but this is not true for path components. Okay, so we will see a counter example in the next lecture. So remark, unlike, so maybe I should make this in red. Yeah, this is an important remark. So unlike the connected components which were closed in X, yeah, the path components need not be closed. So we will end this lecture here.